Okay, guys, can you guys hear me? Give me a signal when you can hear me, okay? All right, so let's give it one more minute while we're receiving more attendance. Today is the first lecture for the new session. Always we have some connection issues, login issues, and most of the students are always waiting for the last minute. So let's wait for one more minute, okay? Yeah, I already see some students having some issue logging in. So like I told you parents, if this is your first lecture, you better give at least 10 to 15 minutes. Make sure you can successfully log in our system. One more minute, let me try to sort of figure out those connection issues. All right, guys, I see it's a 7:01, so let's get started. So first of all, thank you guys for coming here. Welcome to our lecture. In this lecture, we're going to focus on the counting and probability, which is a very important session in the North American math competition. So before we get started, always I would like to spend maybe 3 to 5 minutes, give you guys a quick introduction about our lecture, where we are, where we come from, so on and so forth. I see we have pretty much a lot of old mates, so I'm not going to spend too much time, but at least give you guys a quick recap for the organization, for different kinds of details for our lecture. All right, I'm actually sharing my screen now. Everyone should be able to see my screen. Okay, so at the very beginning, like I mentioned, I want to give you some introductions to our lecture. Our lecture focuses on the North American math competition. So whenever I say North American, it focuses on the American math competitions and the Canadian math competitions. So all the sample questions I will be basically presenting you guys are pretty much focused on the North American math competitions. And also from time to time, I'll randomly pick up some very interesting questions from different regions. Let's say some Chinese math Olympia or some Eastern Europe math Olympia, basically help you guys expand your horizon and try to use the technologies we introduced to do the real problems. Fish and fishing. The most important thing for our lecture is to teach you guys the methodology, the fishing technologies. So for every problem, I'm going to guide you guys how to think rather than basically read the answers for you. So this is actually this is more like an interaction process. And gradually, at the end of the day, I want you guys to show me how you can think during the problem solving process. Okay? So that being said, there are several things which are very important in our math competition lecture. The first one is the interaction. These days, due to the COVID-19, I think pretty much most of the lectures are going to the online virtual lectures. But you know what? The virtual lecture and the face-to-face lecture, they should have exactly the same interaction mechanism. Because at the end of the day, I want you guys to let me know if you understand what I'm saying or not. So think about it. Even though this is a face-to-face lecture, if I ask you questions, you don't reply me, you give me like a poker face, I really have no idea what you think. So in our lecture is actually very dynamic. You can take it as like a regular lecture that you have in your school, so on and so forth. So basically, when you have any questions, you can always raise them up. There are two ways for you to interact with me. The first one is you can just basically unmute yourself. By default, whenever you enter the classroom, I will mute you automatically in order to minimize the, like the interruptions to the lecture. However, whenever you find a question or you have some concerns, you can always unmute yourself. So ask the question, I'll be here to give you a real-time response. Second is, if you prefer a little bit more like a chat, you can basically go to the chat board. I think these guys, and then like, what should I say, these days, you should be very familiar with the Zoom, due to the COVID-19 situation. You can basically, in your control console, you will see 3 dots saying more. As long as you click that dot, three dots. The first drop-down menu is a chat. So that's going to help you to basically type your questions in the chat board. You have two ways to chat with me. Either you chat it, you pretty much put the recipients as everyone, then everyone can see your question or your answers. Or you can choose me as a private chat. In that way, only me and you can see our interactions. If you're a little bit shy, you can always choose for the second option. Right, the first one is interaction. So that being said, I'd better suggest you to have a microphone, right? So any questions, let me know. The second one I want to talk about is the homework. Okay, I believe homework is a very important part for our lectures. This is actually an extension of our lecture. The technologies we introduce in the lecture, we're going to give you some sample questions, basically help you to understand the technology. But after the lecture, you really have to see some real exercise to use the technology you learned to practice more questions. This is where our question section, our homework section comes from. Every week, I'm going to give you 3 to 4 problems as our assignment. You have 1 week basically to finish up the assignment and upload it from the Google Classroom. So for every one of you guys, I have already extended you the invitation. Invite you to go to a Google Classroom where I'm going to post you the materials, the previews, announcement, so on and so forth. If you haven't received the invitation yet, let me know. I'll try to refresh it. So basically, when I will finish the homework, try to upload it from the Google Classroom, and I will mark all your assignment. So for the next lecture, I'm going to pick up 4 students or 3 students, it really depends on the problem, to give us a quick demonstration about your assignment. So trust me, if you did a good job, if you were invited, means that you did a good job. So no worries, I'm not going to make you like a fool. So trust me, if you're invited, you have the correct answer, so try to be more confident. Right? The last one is the presentation. So this is what I actually insist from day one. For every lecture, except our first lecture, I'm going to ask one student to give us a quick presentation. You can find out any questions you like, not necessarily super complicated question or super easy question, whatever question that makes you comfortable. Find out a question and try to, give us a quick presentation. The question should be related to our concepts, right? Now we're in the counting and probability, so any question returned in the territory of counting and probability should be a good candidate. Well, the most important thing I want you guys to do is that, these days, if you only know the answer, that's far away from enough. You need to know how to do the presentation, to think aloud, right? So during the presentation process, hopefully you guys can teach us how to think. Whenever you see such a problem, what kind of buzzword or like the keyword guide you all the way to such a solution? I totally understand, Rome wasn't built in a day, it took 100 years. So the presentation capabilities is also improved gradually by gradually. But nevertheless, let's take this opportunity. Hopefully we can all, get growth in this short summer term, and everyone can basically have some improvement at the end of our 10 session lectures. All right, I think that's a quick, short and brief introduction about our lecture. Any questions? All good? All right. So now we're going to go to the real content. We're going to see the counting and probability. So before we get started, let me try to give you a quick overview of what we're going to cover in our 10 lectures. So in these 10 lectures, we're going to spend the first 2 lectures talking about some basic concepts. Counting and probability is actually one of the 4 very important sessions in the North American math competition, right? We have 4 important sessions: algebra, geometry, counting and probability, and number theory. Actually, this part, like this counting and probability, is very different from the other 3 sessions, because the other 3 sessions, they have numerous formulas, numerous concepts for you to remember. Think about geometry, there's so many theorems. Algebra is even more complicated. You have like different subsessions, and each session you have a bunch of formulas for you to remember. And also the same thing applies for the number theory. However, for the counting and probability, it looks like we do not have so many formulas, so many, theorems for you to remember. So that being said, is actually even more dynamic. You're trying to use a very small group of not formulas or theorems to try to solve very complicated problems. So trying to have a very good understanding about the basic concepts, I think is very important for you to get started. Since this is like a high level lecture, so I don't think I'm going to spend a lot of time talking about basic concepts, which I think you guys should be pretty much familiar before you come to the lecture. But I still take some time, give you guys a quick refresh. If you have any ambiguities, let me know. All right? And then moving forward, we're going to go to a very important concept, which is with what we call the pigeonhole principle. The pigeonhole principle is actually a very, obviously very intuitive concept, and you might understand it after my very plain explanation. And this pigeonhole principle is actually very useful from time to time, especially to the high-level math competitions. We're going to spend almost like one lecture explicitly talking about the pigeonhole principle. And then moving forward, we're going to spend 2 lectures talking about 25 very important types of questions, or we'll say 25 different methodologies in the counting and probability questions. Like I said, counting and probability questions, you have very limited tools, very limited formulas. However, you have so many varieties. But trust me, all those varieties can be classified into one of these 25 different methodologies. I think the purpose of our lecture is trying to give you guys more conclusion, more summary. So at the end of the day, you won't be so just doing like a random walk, right? You have your tools, your technologies, and whenever you see a new problem, this new problem should be able to be classified into one or several types of questions under our 25 big types categories. Okay, we're going to spend 2 lectures talking about this 25 different technologies or different types of questions in the counting and probabilities. And moving forward, we're going to spend another 2 lectures talking about some interesting questions in AMC12 and AMY. You know, different math competitions, they have some preference. People have a memento, right? Everyone has a memento, and the same thing applies for the authors of the AMC and AMY exams. Sometimes people always believe what they believe is correct, right? They believe whatever they believe. So it is always valuable for us to have a more dive into the AMC12 and AMY related counting and probability questions. Let's try to pick up here. Whenever I say interesting, it actually means a little bit difficult. Okay, so some difficult problems from AMY and AMC12, and I have already classified them into several big categories. Let's take 2 lectures, dive into those relatively difficult problems, and hopefully can give you guys an idea, whenever you see the similar questions in the future, what should be your reaction. All right. And moving forward, we're going to spend 1 or 2 lectures talking about some advanced technologies in the counting and probability. So these advanced technologies includes, but not limits to, something like coloring method, some Guy-Fubini method, some continuous adjustment method, or some like induction method. These kind of technologies are considered to be the high-tech technologies. You might not necessarily see them on a daily basis, but I think we'll take this opportunity, help to expand our horizon. So try to see this problem, see the real applications of those problems, and try to give you guys a little bit, kind of like a hint. So in the future, whenever you see any new problems from any kind of math competitions, you might say, okay, this is kind of like a deja vu. I said the problem before, so hopefully it give you guys a quick heads up, right? And then in the last 2 lectures, we're going to talk about, one is the binomial theorem, which is actually a very important theorem. It will be tested from time to time. And also we're going to talk about the probability, okay? So the probability, we're going to focus on 2 types. One is the classic probability, which pretty much everyone knows that, while the other one is the geometric probability, which is kind of a favorite for the AMC, right? Especially for AMC, they love to test you the geometric probability, using the area, using the volume, try to determine a certain type of probability problems. All right, so this is pretty much a short and brief, quick overview, like kind of forecast about our 10 lectures. And we're going to go to more details whenever we're getting there. All right, any questions? All good? Okay, if all good, so let's dive to our first lecture. We're going to talk about the basic concepts of counting and probability. All right, counting and probability. See, I think the name really speaks for itself. The number one important thing is you need to know how to count, right? They're going to start with count. Well, before we jump to the permutation, combination, all those kind of fancy concepts, I think whenever you want to count something very intuitively, how to do the count, I think people have some basic ideas. My understanding is count, you basically have two things. One is you do the exhaustion method. You just count them one by one, right? You have 200 guys, okay, counting them one by one. So this is like exhaustion method. I think there's not so much flowery things I want to talk about. Well, the other way to count is kind of try to find out a pattern, right? Try to find out some kind of like a representative before you blindly counting out everything one after another, right? Try to find some pattern. Try to basically find out the representative for each of the pattern and do the counting from there. I think this is quite understandable. And then before we jump to this part, let's step back a little bit from our high vision, the entire whole vision of the entire mathematics. For the entire mathematics, we're basically talking about three types of problems. Okay? For the entire mathematics, we're talking about three types of problems. The first type is elegant, and you have a pattern. You know, some problems is very elegant. It might be very complicated. However, you can find a pattern. For instance, I gave an example. So I don't know if you guys are familiar with the Taylor's expansion. So sin x, right? Sin x can actually read as what? Written as a sum of different polynomials. Let's say sin x can be written as this, right? It's cube 3 factorial x5, 5 factorial x to the power 7, 7 factorial, all the way minus 1 to the power of n, 2n plus 1, factorial, x to the power of 2n plus 1, right? This is the famous Taylor expansion, or you can say Taylor series, right? The same thing not only for sin x. Any kind of x can be denoted by using a series of polynomials. You see, this is a complicated problem. However, we have a very elegant pattern. The same thing applies if you guys are familiar with the quantum mechanics. So I don't know, because different people that go to IB or AP, whatever things. So if you're familiar with the Schrodinger equation, this is a famous equation for the quantum mechanics. So this is one of the expressions for the Schrodinger equation. I'm gonna help you write this. Just try to expand your horizon. So this is the Schrodinger expression, E phi, right? So you know this is actually what? This is actually called the Laplace operator, right? And this is actually a what? A wave function. I don't know if you guys are familiar with this or not. So this is like a very complicated function. However, this function has a very elegant solution. The solution goes like this. Maybe you don't think it's very elegant, but trust me, in the eyes of the physician and also like the mathematicians, this is a super elegant solution. M factorial gamma m plus alpha plus 1, 1 x over 2 to the power of 2m plus alpha. Here, this is the famous gamma function. Okay, this is one type of problem. Very elegant, very complicated, but you have a pattern. Okay, this is type number 1. Type number 2, you might not be so lucky. There are some complicated problems. However, there's no pattern. The very good example is the value of pi. right? This is a complicated problem. You know, this is like this is kind of irrational number, and there's no way for you to basically know how many digits, right? And same thing applies for the e, right? The e value. So, these kind of problems, unfortunately, there's no pattern. It's very complicated. I don't think you want to see them in the math competition. And trust me, you're probably going to see them in American Got a Talent or something, the kind of like talent show. You can remember like I don't know, like 10,000 significant bits after the pi, after like the decimal, so on and so forth. But this is kind of no pattern. Okay? This is not exactly what we want. Well, the third part is actually there are some pattern, but not necessarily applies for every single element. Let's say we have maybe 100 elements, maybe some of them follow one pattern. The other part follow another pattern, and then the other part follow another pattern, right? This is quite understandable in our everyday life. So this part is actually one of the favorite things in a math competition. So when I'm saying this, let's say whenever you have all the patterns, one single formula, list them out. That's it. Whenever there's no pattern, unfortunately, we can do nothing. But if there are some patterns, maybe I can try to list them out, right? List out. But I don't have to list out everything one by one because they have some patterns. Let's say pattern 1, I can list out several things. Pattern 2, I can list out something, so on and so forth. And this is actually a favorite from the math competitions perspective. And the technology we're using to list out number pattern 1, list out pattern 2, all the way list out pattern n, in mathematics, we have a professional word for it. So we call this enumeration. Okay? This is called enumeration. If you do some Google, what does enumeration mean? Enumeration means list them one by one. However, in a more organized way, in a more patternized way, not randomly list out one after another. Okay, so based on my explanation, maybe you already figure out something. Whenever you do the enumeration, the most important thing or the million-dollar question for you guys is try to find out what is the pattern 1 and what are those representatives for pattern 1. What is pattern 2? And what are the members for pattern 2? So on and so forth. What is pattern 3? And what are the members for pattern 3? And this process, we also give it a name, a casework, right? You try to break them into different cases. Okay, so that being said, enumeration plus the casework is actually a very good technology for us to basically find out, okay, what are the patterns and what are the representative for all those patterns. Okay, I think this is quite understandable. So here looks like we have a million-dollar question is, okay, how can I do the casework, right? I think for the same thing, you have many ways to do the case, right? Maybe in some way to do the case is much more complicated than using another way. So the million-dollar question left for you guys is try to figure out how to do the casework, right? There's any technologies or guidelines for you to do the casework. So I have already summarized into one word. That is a smart classification. Maybe 2 words, right? A smart classification. When you want to classify the very complicated things into different cases, the most important thing is you want to do a smart classification, a smart casework. So what is the criteria to be a smart classification? I actually have 2 words for them. One is no overlap. The other one is no oversight. Yeah, in Chinese we say 不重不漏. Or in English means no overlap. Means let's say you break them into several cases. For different cases, there must be no overlap. Everything you already discussed in case 1 shouldn't be discussed in case 2 for the second time, right? Otherwise, you have some duplicates. I think this is quite understandable. The other part is no oversight. Whenever you classified everything into, let's say, 5 different cases, hopefully your 5 different cases already covered everything. If there are some things still not covered in these 5 cases, means you have some oversight. Is that right? So your thinking process is not comprehensive enough. So that being said, in the future, whenever we do the casework, we always try to make sure no overlap and no oversight. So don't be panicked. Later, I'm going to give you more examples, then you will get a hang of it, how to make sure your casework can be 100% no overlap and no oversight. All right? I think this is like a basic technology for the enumeration. Like I said, enumeration, you're just counting them one by one. Everyone knows how to count from your kindergarten, probably. So I don't think there's too much meaning that we're going to spend too much time talking to us how to do the count. So moving forward, let's try to do some real problems. From the real problems, right, let's try to figure out how you're going to count for those real situations. All right? Let's go to an easy problem first. As icebreaker, question number 1. As shown in the diagram, Peter starts from A point to B point. He can only walk to the right and to the south. Please determine how many ways he can move from A to B. I'll give you the graph here. This is A, this is B. Okay? As you show in the diagram, Peter starts from A point all the way go to the B point. So basically every single step, he can only move one step, right? So, but whenever he moves, there's kind of a constraint. He can only move to the right and to the south. It means he can either here, something like here, right? However, he cannot move up or move back, right? He cannot move to the left or he cannot move north. All right? So with all those information provided, please try to determine there are how many ways for Peter to move from A to B. Okay? I think this is a fairly straightforward problem, right? Everyone should calculate out fairly quick. Yes. So let's try to, for those guys, let's try to be patient a little bit. This is an easy problem. So use this problem, try to introduce some complicated concepts. So this is kind of like, from A to B, what are you going to do? You have to figure out how many ways, right? So intuitively, enumeration, you have to count how many ways one after another. But how do you want to do the count? Think about it. This is actually a very important technology you want to use whenever in the math competition. In all the counting and probability related problems, sometimes it's always easier to do some reverse engineering. Whenever you want to think of the problem, maybe try to think about it from the very end backward. Think about it. Peter can only go for such a way, right? Going down and going to the right. So in order to go to B point, before he go to the B point, he can either work from here to the B point or work from here to the B point. Is it correct? So that being said, there's no way that he jumped from here to here, right? He must be able to walk from, this is, let's say, I want to call A prime, or I want to call from B prime. So as long as you figure out how many ways for Peter to go from A all the way to A prime, how many ways that Peter can go from A all the way to B prime, then adding those two numbers together, then you will be able to figure out what is the total ways for Peter to go from A all the way to B. Is that right? So that being said, if I can figure out for every point within this grid, how many ways for Peter to achieve there, that's going to be easier for me to calculate them out. All right? So I think we just do some enumeration. Let's try to list them one by one. Let's say for Peter to go to this point, there's only one way, right? He just basically move to the right. Same thing to go to this point. Same technology, he can just only move straight, right? There's only one way. Same thing here, one way, get to this point one way, get to this point one way. There's no way around. You just basically move straight ahead. And same thing applies if Peter wants to walk in this way, also only one. Is that right? Anything to the edge of this rectangle, there's only one way for Peter to basically walk. But as long as Peter want to go to this guy, he can either go from here or go from here. Only two ways, no other way around, right? So basically, how many ways you can get here is actually two. Then come to here. He can either go from here, he can just basically, let me change a different color, from this point come to here, or from this point come to here. No way around. Is that right? Since there are already two ways for Peter to come to here, so to come to this part, there are actually three ways. Okay, I think that's quite understandable. So that being said means what? As long as you can do an add for these two adjacent diagonals, then you will be able to determine how many ways Peter will have in order to come to here. Is that right? So that part, 3 plus 1, 4, 5, 6, 6, 10, 15, 21, 4, 10, 20, 35, 56, 5, 15, 35, 70. So here is 160. Is that right? So this is like the basic counting. You're not using any technology. You just basically list them out using the enumeration. So that being said, okay, there are actually 126 ways for Peter to walk from the A point all the way to the B point. I see pretty much everyone has the correct answer. This is kind of like an easy problem, right? All right, this is actually I think this is like the more primitive way. We do the counting one after another, right? We actually have another more straightforward way. So this is solution 1. We really want to do the counting. Let's go to solution 2. Is there a more straightforward way for us to figure out how many ways from A all the way to B? Instead of doing this kind of counting one by one, is there a more analytical way for us to figure out how we're going to let Peter to go from A all the way to B? Think about it this way. At the end of the day, regardless how Peter walk, Peter is going to do what? Let's try to do from here. Peter is going to go here. Let's change the color. Go right, maybe go down, go right, go down, go right. Something like this. So that being said, in order to get from A to B, in total, Peter has 9 steps. Right? Must go to the right and go to the south. There are only 9 steps. And within these 9 steps, how many steps Peter needs to go to the south? South step. Of course, at the end of the day, he will go for 4 steps to the south, because at the very beginning, Peter is standing here. At the end of the day, Peter is standing there. He must move 1, 2, 3, 4 steps to the south, right? And also, how many steps he needs to right? He basically has to move to the right. 5 steps, right? 1, 2, 3, 4, 5. But of course, they don't have to be in the same order, right? He can be south, basically south, right, south, right, right, south, south, or south, south, right, 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 so on and so forth. But regardless, in total, he has to move 4 steps to the south, 5 steps to the right. So that being said, what I'm trying to do, something like this. I'm going to have S, 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 4S. I'm going to have R, 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 5 Rs, right? If I close my eyes, I let them to do a full permutation. That's going to be what? 9 factorial, right? So south, SRRS, SRS, whatever, I don't really care. But think about it. All the S, they're actually the same. And all the R, they're actually the same. So therefore, I have to exclude 4 factorial and 5 factorial in the denominator. Is that right? Because at the very beginning, when I do the 9 factorial, means what? I assume every single element, they are different, right? S1, S2, S3, S4, R1 all the way to R5. So therefore, that's going to give me 9 factorial in the numerator. However, it does not have to be, because all the S are actually identical. All the R's are actually identical. So 4 factorial, they're actually exactly the same, duplicates. 5 factorial, so many R's, their permutation is actually duplicate. So 9 over 4 factorial times 5 factorial. That will give you 126. That is actually the shortest way to solve this problem. Okay? So far, so good? So this is kind of like an extension, right? A very basic problem. Any kind of this grid-related problem, 2 ways to solve. Using the enumeration, counting them one by one, or try to use what? Some quick analysis. All right? I think this is quite basic problem from question number 1. Okay, let's do a little bit of extension. Extension 1-1, right? We're trying to use the same problem, but try to give you guys as much concepts as possible. If it is exactly the same problem, Peter wants to move from A all the way to B. However, today there's a flood. Okay, there's a big rain, there's a lot of flood. So therefore, in this kind of pattern, in this routine, there is kind of a mud pond. Okay, means some areas that Peter cannot really reach. I'm going to give you an example. Maybe something like here. I have something like here, okay? Now, I have some mud pond. Means all those shadowed area, Peter cannot go. But for the other areas, people can go as well. In that case, who can tell me how many ways that Peter will be able to walk from A all the way to B? Think about it. Every single problem, we're going to do a little bit of extension, understand all the scenarios. For now, there are some barriers, right? You won't be able to cover all the points. In that case, who can tell me how many ways I can basically walk from A all the way to B? Yeah, I see some students, they have the correct answer. Okay, trust me, this is not a huge jump. There should be a tiny, tiny tweak, and you should be able to solve it out. So the question says you have some mud pond. A mud pond means what? You cannot really reach. So these points under the mud, you can no longer reach out, right? So let's do a comparison. Previously, I have already listed out all those mapping. I think the mod is actually here, right? Okay, under the mod, previous, let's say at this point, change a different color. Let's say at this point under the mod, previously I have a number 10, means there are 10 ways to go to this point. Let's say at this point, I also have a number 10, means there are 10 different ways to reach this point. But who can tell me what's the difference as long as I put a mod on this point? What has been changed? From mod and no mod, what has been changed? Think about it. The only thing that has been changed is that previously there were 10 different ways to get to this point. But however, at this moment, there's no way to get this point. Is it right? So that being said, previously at this point, I have a value 10. But for now, this 10 has to be changed into 0. Is it right? Previously, this point has a value 10, but for now, no one can reach out this point. So this guy can actually go to 0. So that being said, okay, every point that has been covered by the mud pond, for now, there's a 0 way for you to get there. 0, 0, 0, 0. All right? However, outside the mud pond, nothing has been changed. You still have one way to come here, one way, one way, one way, one way, one, right? This is going to be 2, 3, 4, 5, right? Nothing has been changed. But for now here, let's say previously I need to add those 2 points together. For now, I'm going to do the same thing. 5 plus 0, give me a 5. 5 plus 0, give me a 5, right? Here, this is going to be 1, 1, 1, 6. 2, 3, 4, 10. You see, you just simply cover how many points? 6 points. Let me change a different color. You simply covered only 6 points by using a mod pond. However, you are reducing your number significantly. At the very beginning, you have 126. But now you reduced significantly only to 10 different ways. All right? So covering amount changed nothing, but you basically switch the number from whatever it used to be into 0. And then you're good to go. Okay? So far, so good? Okay, if all good, let's go for another extension. Any question, please let me know, okay? Any question, let me know. Let's go to another extension, 1-2. You know, for now, I'm actually giving you a relatively smaller grade, right? It does not really having. So somebody have a question. How do you solve this question using solution 2, as in using combinations? Yeah, Victor has a very good question, and that's exactly what I'm going to tell you in the next step, extension number 2. So for extension number 1, we said we have a relatively smaller, it's like 4 times 5 grade, right? Like the numbers are relatively small. But what if I give you a huge, huge number? I give you like a big grade. If you want to do the same thing, I think you can still do that. But unfortunately, you're going to take a lot of time. And also, you're going to be very careful when you do the calculation. Do not do the wrong calculation. If you have a tiny typo for one thing, you're going to mess up. This is more like domino effect, right? You're going to mess up everything that behind. So do we have something more straightforward for us to solve a complicated problem? Let's say I give you 100 times 100. What are we going to do? How are we going to solve them in a more straightforward way? That's actually my extension number 2. So extension number 1 is more like you are counting, right? Extension number 2, let's do some calculation. Can I use a calculation way to calculate this fairly quick? That's actually a problem from, oops. That's actually a problem from here. Try to put it here. Okay. We're looking at a problem from 2010 AMC 12A, question number 18. This is exactly the same thing we're talking about today. The question says there is a 16-step path to go from -4, -4, all the way to 4, 4. It's kind of like a big matrix. Well, each step increasing either the x-coordinate or the y-coordinate by 1. So basically, you're starting from here, let's say A, all the way to here, B. You can only go for the right and go for the up. Same thing, right? And how many such paths stays outside or on the boundary of the square -2, +2? Look, this is almost the same thing as we find here, right? So -2, +2, something like here. Okay. Something like here, right? You have a shadow here. This is like the mud pond, right? You want to make sure that you go from A all the way to B without touching the one in the middle. Okay, one way is use exactly the same thing we did before, right? Well, let's try to do a little bit dynamic because in AMC, you don't really have time, right, to do such like all the numbers, adding them together, and you also made some mistakes. So a problem like this, we'll try to use the analytic way to solve this. I want to go from A to B, and I don't want to touch anything within the little shade, right? Like the little shadow area. How can I figure out, how can I walk in order to make sure I'm not going to touch in this? Well, the question says what? The question says you can only walk up and work to the right. So think about it. I just want to give you some example. Let's say for some reason I go to here. As long as I reach the point C, from C point, I can only go up or go to the right, right? So that being said, there's no way for me to touch the entire shadowed area. That makes sense. As long as I go to this point, let's say D, again, I can only go up, I can only go right from D, so there's no way for me to touch anything in the shadow area, right? Let's say I go to this point, let's say E. Okay, if I go to the E point, again, from this E point, I can only go up, I can only go to the right, and there's no way for me to go into this problematic area. Is that right? However, let's say, if I go to this part, I don't know, maybe F, then there's no guarantee. From F, if I go to the right, I might be able to enter this problematic area. But if I go up, okay, my problem can be solved. So it looks like F is not always a safe point, at least not as safe as CDE. Is that right? Okay, so I'm gonna drop this F. Who can tell me, is there some other points also can help to secure the fact that I will never step into the region of this shadowed area? CDE, I think, is perfect, right? Is there some other points? The same thing? Let's say if I come to here, can I make sure I will never touch the problematic area? Of course not, right? Okay, I see Henry has the correct answer. -3, +3, -3, something just basically like here, right? Let's check it out. As long as I go to this point, taking from there, I can always go up. Oops, sorry. I can always go up, and I can always go to the right. So there's no way for me to step into this problematic area. Same thing, as long as I come to here, I can always go up. I can't even go right? Always go up. So there's no way for me to step into this problematic area. What else? Is this a comprehensive thing? Check out the question. Yes. The question says what? How many paths you can make sure that you can stay outside or on the boundary of the square? On the boundary of the square is also correct. So if I come to here, think about it. If I come to here, I can only step up, I can only step right. Also, there's no way for me to enter into the region, right? Into the problematic region. So that being said, okay, this point is also a safe point. Let me try to give the name. Maybe I'm gonna call this F. I'm gonna call this G. I'm gonna call this maybe H. So that being said, as long as from A, you go to C, you go to D, you go to E, you will for sure to bypass this, I don't know, this kind of region from the upper area. And the same thing, if you go to F, you go to G, you go to H, you will also guaranteed you can bypass from the lower region without touching these blacked out region. Is that right? So this is actually based on our analysis. So try to understand, whenever you figure out this is actually the casework. This is actually the casework. Is that right? It basically shows you break down your random walk into 6 different scenarios. And these 6 different scenarios can make sure you will pass this blackout region without touching the inside of it. So if you ask me what to do the casework, how to do the casework, this is the way how we're going to do the casework. We break down a very vague problem into something more tangible, more substantial problem, right? So if I go to A to C, A to D, all the way A to F, I can guarantee there's no way for you to touch the blackout area. If you know the casework, that's fantastic. Let's jump to there. Let's have a look how many ways you can go to C, D, E, F, all the way to G. Okay, first one, change the color, A to C. From A to C, and then from C to B, right? Of course, you're at the end of the day, your target is trying to go to B, it's not go to C. From A to C, there's only one way, up, 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 up. From C to B, same thing, one way, up, 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 no way around. So you only have one way to get from A to C, from C to B. All right, so let's try to erase this guy. From A to D, from A to D and from D to B, basically you're doing 2 steps. Step 1, you want to do from A to D. Step 2, you want to D to B, right? Think about it. From A all the way go to D. Let's check out this. Use the technology we just introduced in our previous question number 1. To get from A to D, you have to work up 1, 2, 3, 4, 5, 6, 7. You work up 7 steps, and then you work right 1 step, right? 7 up plus 1 right. In total, you have 8 steps. Is that right? Well, this 8 step, you can choose the first one you go to right and then up, up, up. Or the second one you go to right, up, up, up. Or the third one go to right, up, up, up. But as long as you're going to achieve from A to D, you must choose 1 step to go to the right. While the other 7 steps, you go to the up. You have no other choices. So there are how many ways? Oops. 8 different ways from A all the way to D. Is that right? Same thing applies. from D to B. From D to B, you have to go up one step. 1, 2, 3, 4, 5, 6, 7. Exactly the same thing. You have 8 steps in total, 7 steps to the right, only 1 step to the up. You can choose where you want to place this step. So you have also 8 different options. Is that right? So that being said, you have 8 square from A to D, from D to B. It's quite understandable, right? Okay. So who can tell me from A to E, how many steps? And then from E to B, how many steps? Who can tell me this? A to E, E to B. Yeah, I see somebody has the correct answer. 28. Why? Same thing. In order to go from A to E, you have what? You have 8 steps in total as well, right? You have 8 steps in total as well. But here you have to walk 2 steps to the right and 6 steps to the up. So from a combinations perspective, you just have to do a C8-2. From this 8 steps, you tell me reach 2 steps, you want to go to the up. So far, so good? Quite understandable, right? And then from E to B, exactly the same thing, right? From E to B, here, you have also 8 steps in total. You want to pick up 2 steps to the up and 6 steps to the right. Again, C8-2. In total, you'll be doing this C8-2, perfect square. By the way, I want to have a quick clarification. And in our North American, whenever we talk about the combination, let's say you want to choose 2 from 8. You actually have 3 ways to write it. You can write as like apprentice, 8-2 means you choose 2 from 8. You can use C8-2 means you choose 2 from 8. You can even use 2C8 to choose basically 2 from 8. You know what? People will understand either of them. You choose whatever the fix feels most comfortable to you, right? For me, I'm more comfortable using this guy, C8-2. But for you guys, you choose whatever you like. So that's actually what? C8-2, perfect square. Okay? And I think all the way from here, you don't have to calculate too much. Because as long as you have already figured out how many ways to go to C, how many ways go to D, how many ways go to E, whenever you calculate the following part, F, G, H, they're actually what? Symmetric. Is that right? The way you go from, let's say I'll change a different color, from A to C, from C to B will be exactly identical from A to H, from H to B. Is that right? Change a different color. The way you get from A all the way to D, from D to B, will be exactly identical from A to G, from G to B. You see like the diamond shape. And the way you get from A to E, from E to B, will be exactly the same from A to F, from F to B. So that being said, this guy will be the same as this guy. This guy will be the same as this guy. This guy will be the same as this guy. Is that right? So in total, you're trying to add all those scenarios together. 1 plus 8 square plus CA2 square plus. So the total number is 1698. 1698. All right? So think about it. 1698, that's a big number. If you really want to list out one by one, they're probably going to take some time and you might have some calculation error. Okay? So this is actually the solution for this problem. For this problem, I want to remind you two things. Okay, every problem, we only have a limited problem, but I want to give you as much as possible. The first one is how to use the casework to do any kind of like a mud pond or like shadowed area, whatever you call it, whatever you name it. Always try to break them into different cases. Okay? Second part is you always try to use some symmetric property. You know, later with our lecture move forward, you're going to have more and more ideas. A lot of continuum probability problems, you need to use the symmetric property. Okay, this kind of symmetric property can help you significantly reduce the complexity of the problem. All right, so far, so good? Any question? Any question, please let me know, okay? You can privately chat with me so no one will see your question if you feel a little bit shy or something, but you don't have to. All right, so, okay, we start from an easy problem and then we jump twice. So this is a problem from AMC12. Trust me, try to do this kind of pass from one place, go to another place, how many ways, how many scenarios. This is a favorite for the AMC and Amy. Since we are familiar with this, let's go for Amy problem. Let's have a look for a little bit complicated problem, how we're going to do the discussion. Oh, good. So the next problem we're looking at is a problem from 2017, Amy 2, question number 11. Before I jump to the explanation for this problem, I want to give you a quick heads up. For Amy problem, Amy has like 15 problems in total, right? Not always question number 15 or question number 14 is the most difficult one. This is difficult. This is kind of different from AMC. AMC normally 25, 24 is the most difficult, right? But Amy is different. Most of the time, question number 11 to question number 13 is the most difficult in Amy, okay? Because this is how it works. So normally people do is like linearly, number 1, number 2. So they will spend most of the time stacking with number 11 and number 13. And they don't really have time to check number 14 and number 15. But you know what? Most of the time, not say most, I'll say like a decent amount of time, number 15 is actually way more straightforward than number 11 to number 13. So this is actually the most challenging part in the Amy. Just for your information, if you get stuck, maybe jump to the last 2 problems. They're a little bit more straightforward than number 11 to number 13. Okay, this is a little bit different with the AMC. Okay, let's have a look. So the problem says what? You have 5 towns. They're connected by a system of rows. There is exactly 1 road connecting each pair of towns. Find a number of ways there are to make all the roads one way. Okay, this is like a one-way road. In such a way that there is still possible to get from any one town to the other town using the roads, possibly passing through all the other roads on the way. Okay, so basically saying what? You have a bunch of towns, they're connected by, sometimes it's unidirectional, sometimes it's bidirectional. Okay, this is only like unidirectional. Excuse me, all the roads one way, right? There's only unidirectional ways, right? Connect all the towns and try to find out, okay, if you have a such arrangement, I can start from one way, one town, go through all the other town. Okay, please tell me how many arrangement you can do such a way construction. Okay, so this is the problem. So I'm gonna draw the problem something like this. 1, 2, 3, 4, 5. I don't know, something like this. And the question says, there is exactly 1 road connecting each pair of the towns. Means every single 2 tongues, they must be connected, right? Every 2 tongues in the 5 tongue, they must have 1 row connecting to them. We have 5 tongues, and every 2 of them have a connection, means in total you have C52, which is what? 10 rows. There's 10 rows connecting these 5 tongues. And the question is asking you, okay, all those 10 rows, they are directional. Can go here, can go there, I don't know, just gonna give some random things, okay? But after your arrangement, you can always start from one tongue, then go to the other tongue. Please try to tell me how many arrangement you can do using such an allocation. Okay, how many scenarios you can do using such an arrangement. So if you're familiar with like the regular math competition concepts, at the first sight of this problem, this is a graph theory problem, right? This is a graph theory problem. You're trying to find out, basically, you're trying to traverse a graph from one point, go to the other point. Okay, well, the question is that you need to give me some idea how to make this road allocation such that I can start from one tongue all the way, go to the other tongue without any interruption. You know, a problem like this, always we need to think, how do we think? This is $1 million question we're going to ask you guys from here all the way to the end of lectures. This looks like a very complicated problem. You have 5 tongues, and for each tongue, you actually have 4 rows. They can come in, they can coming out, regardless whatever, right? And you want to see that how you can walk from one, let's say from A to B. Maybe, to directly think this problem is too complicated. Every single tongue, there are 4 rows, and the rows has directions, so on and so forth. But let's try to do a little bit like, what should I say, on the other side of the problem. If it is very difficult to figure out how many ways to do from one tongue to the other tongue, right? How many like possible ways? Is it possible you guys can tell me in what kind of allocation you can make sure you cannot work from one tongue to the other tongue? Let's say if you want to give a negative example, who can tell me in what kind of arrangement I can make sure there's no way for you to jump from one tongue to the other tongue? Who can tell me this? Tell me what is the possible arrangement to make sure this is not going to happen. This is actually the proof by contradiction, right? Okay, I see some students have some ideas. If I have a tongue, all the 4 rows are going in. For sure, this is not going to happen, right? As long as go to this tongue, there's no way for me to get out. Or I have a tongue, all the 4 rows are going out. As long as I go to this tongue, I mean, there's no way for me to get to that tongue, right? Because all the rows leads out. I think this is quite intuitive, right? You don't need a PhD degree to get this, right? This is kind of very understandable. Okay, this is actually, as long as you see this, you're actually opening a door to solve this problem. In order to make our life easier, all the rows going in, all the rows going out, this is more like a human language. Let's try to give you a professional words. To say something like this, everything goes in, I want to say the yin degree equals to 4. This is actually a professional graph theory word. Yin degree in the graph theory means how many paths they're actually going inside, how many sides they're going inside. This part I give you another name, out degree, also equals to 4. This is only to make our life easier, rather say go in and going out, right? As long as I have a point, yin degree equals to 4, or I have a point, out degree is equals to 4, I can make sure there's no way to cover them all. Right? This is quite understandable. Actually, for this problem, as long as all the times the in degree out degree, they're both greater than 0, then there must be a way to traverse all the tongues. This is actually a conclusion. For this problem, not only for this problem, for all the graph theory, all these tongues related problem, as long as you can make sure every single tongue, their in degree and their out degree are both greater than 0. Means there are something goes in, there are something goes out. I don't really care. 1 goes in, 3 goes out, 3 goes in, 1 goes out. It doesn't matter. As long as you have some goes in, some goes out for every single tongue, you will be able, or there must be able, to figure out a way to traverse all the tongues from one point to the other points. Okay? How to prove this? Trust me, to prove this, you need a comprehensive graph theory related knowledge. This is not going to be possible within this Amy's time. But we can do some intuitive explanation. And I want to give you one example, intuitive example, try to give you guys, help you guys understand how this works. Okay, give me an example. Let's say I have a A, I have a B, okay? So C, D, E, okay? C, D, E, okay? So at the very beginning, let's say I have B is pointing to A. I want to make sure how I can write. I can walk from A back to B, right? From B to A is already given. And how to go from A back to B. As long as I figure it out, I think this is understandable for you guys to see how we're going to traverse for all the 5 tongues. Okay, so I'll give an example. Let's say I want to also do a E to A, everyone pointing to A, right? Okay, think about it. Let me try to do a line from here. Because let me try to see if A is pointing to C, for instance. If B is pointing to C, if C is pointing to B, okay, my work is done. A to C, C to B, right? So I'm not going to make it happen. I want B pointing to C. Okay? Okay, so C to E. If I let C go to E, and then E go to B, okay, this is going to be my work is done, right? So I'm not going to let it happen. Something like this. I'm going to let E go to B, but I'm going to let to E go to C. Okay, I just want to make your life difficult. Okay, so C go to E, E go to B, your work is done, right? Okay, I want E go to C. Okay, you already have 3 things pointing to C. According to our definition, we must have every single tongue, the in degree greater than 0, the out degree greater than 0. You already have 3 things, 3 rows pointing to E. So the last row must pointing out. So here, C must be pointing to D. Okay? Going to D. If I D pointing to B, of course, C, A will go to C, will go to D, will go to B. So your work is done. I'm not going to let it happen. I want to let D pointing to E. Think about E. E already have 3 degrees going out. The out degrees of E is already 3. So there's no way for you to do a E go to D, right? So you must have E being point from D. Let me try to erase it. So the last one must be from D to E. Otherwise, there will be everyone going out from E point. Is that right? So that being said, as long as you give me such arrangement, now you'll be able to see from A to C, C to D, D to E, and E to B. So you'll be able to find a closed loop. You guys follow me? So far, so good? Please give me some feedback. Yes or no? Can I have some feedback? Okay. Because we won't be able to give you a very comprehensive proof, very rigorous proof. We just want to give you some example. You see, in such an example, you'll be able to see, okay, regardless what you're going to arrange, as long as you have not all the points, all pointing in or all pointing out, as long as you have some pointing in, some pointing out, you'll be able to basically cover from A to B. Okay? So here, I want to give you a side talk. So you're actually talking about a graph. So these are all the points, right? If you want to do a traverse to the graph, this is actually, so you're talking about a traverse, right? From one point all the way to the other point, and maybe from A to B, from A to E, so on and so forth. Trust me, this is a very, very important topic for the graph. How to traverse all the elements in the graph along your size. This is a significantly important topic for the entire graph theory. And there is actually a very famous, what should I say, like a problem or conjecture. Okay, so that one has actually tried a lot of attentions in the last hundreds of years. You guys can do a Google search. The topic is called the famous 7 bridges of Königsberg. Try to Google this. 7 bridges of Königsberg. This is actually one of the famous complicated problem these days for us to figure out. Okay, this is actually a very famous problem. So basically, so like the same thing. They have like different island. There are they have a bunch of island, and there are 7 bridges connecting all those islands. Try to find a way that you can traverse all those islands using the 7 bridges. This is like a world-class problem for the graph theory. So that being said, means trying to figure out this is actually something very challenging. Okay, so now we kind of having like an idea. Okay, as long as this is our conclusion, just want to give you this conclusion. As long as all the points, every single times, I have something coming in, the in degree is greater than 0, the out degree is greater than 0, I will be able to figure out everything. I will be able to traverse like all the tongues basically in the arrangement. Okay, we're on the same page. Again, how to solve this problem, right? Like we said, in order to find how many ways you can basically, from one way go to another, and then go to another, maybe there's so many scenarios. So let's try to think about the other way around. How can we find the opposite? If in this arrangement, there's no way for you to traverse all the roads, all the towns, and then you use the total number to do a subtraction, you'll be able to solve this problem, right? If we do the positive one, we cannot work. Let's go to the other side. Try to think about the negative scenarios. Okay, so casework. Our casework starts from here. In my casework, I'm trying to find out which pattern does not work, right? I'm going to find out all the does not work patterns. So intuitively, if I have one tongue, the in degree is equal to 0, is equal to 4. The out degree is equal to 0. That's pretty much what we mentioned previously. In that way, there's no way for you to traverse all the graph, right? Think about it, 1, 2, 3, 4, 5. Let's take one row. In degree is 4. 1, 2, 3, 4. Think about it. We only have 5 tongues, and one tongue in degree to 4. This kind of tongue, there must only one, right? You can't have 2 tongues, both of them in degree equal to 4. You see, those guys already contribute this in degree to make it to 4. So that being said, there's only one tongue from the 5, you will be able to make sure the yin degree can be go to 4. Right? And for the rest, you have how many terms? You have how many rows in total? I said you have 10 rows in total, right? C52. These are the total rows after you finish the construction. C52. In total, you only have how many rows? You only have like 10 rows. Okay. Now you already construct 4 rows. Your remaining 10 minus 4 equals to 6 rows. For this 6 rows, you don't really care. You can be 1 to 2, 2 to 1, 1 to 3, 3 to 1. You don't really care, right? So that being said, for the remaining 6 rows, you have 2 to the power of 6 different scenarios. So far, so good? This is actually 1 term. The in degree is 4. The out degree is 10. And then like the out degree is 0. Okay? Case number 2. 1 term, same thing. In degree 0, out degree 4. Exactly the same thing, right? Have a 1 term, 1, 2, 3, 4. You have 1 term. It's actually pointing out to everyone. No one is pointing to him, right? It's pointing out to everyone. It is exactly the same thing. From this 5 terms, each term will be chosen as this out degree equal to 4. And for the rest of 6 rows, you take whatever you want to take. So far, so good? Well, we cover all the scenarios? Or there might be some other more complicated scenarios remaining. There's actually a more complicated scenario. You said there's 1 term, in degree to 4, out degree to 0. You said there's 1 term, in degree 0, out degree 4. But it is quite possible there might be some combinations. You might have some terms in degree 4, some terms out degree 4. This is the most complicated part. You guys follow me? Some students ask, why do you multiply 2 to the power of 6? Yeah, because like I said, there are in total 10 rows there, right? 5 terms connecting to all, there are 10 rows there. You already take 4 rows to do your in degree 4 or out degree 4. So remaining 6 rows. The 6 rows, I don't really care. You do whatever you like. Can be out, can be in. So each one you have 2, all the way you have 6 twos. So 2 to the power of 6 using the multiplication principle. Is that right? Okay, any question, let me know. I'm here to help. Okay, so the most complicated thing is our scenario number 3. I have some tongues, not some tongues, but some tongue. Their in degree is equal to 4. I also have some tongue. Their out degree is 4. They are existing at the same time. We need to figure out what is the number for this scenario. This is, I think, the most challenging part in this problem, because this is an Amy most difficult problem. You use different kind of technologies together. We're gonna actually use this, the Venn diagram. In the set theory, the Venn diagram. Think about it. If I close my eyes, I have 5 tongues. You have the tongues. I have 10 rows, right? If I close my eyes, in total, I should have 2 to the power of 10 different scenarios. Every 10 rows can be here, can be this way, can be that way, can be in, can be out. In total, I have 2 to the power of 10 different scenarios. And in these scenarios I just mentioned, there are some scenarios. Let's say the in degree equals to 4. This is our number 1, right? And I also have some scenarios. Their out degree equals to 4. This is our second scenario. And the size of these two subsets are actually the same. C51 times 2 to the power 6. So the $1 million question is here. Okay, the overlap part is the part. Still, they have some terms in degrees 4. They have some terms out degrees 4. Please help me to determine what is the number of those guys. What is the number of those guys? As long as you know the number of those guys, the question asks you to, what is the valid area? So everything here is actually the valid scenarios. Is it right? Using our Venn diagram. All the green area is the one that works. You can make sure there's no in degree 3, no out degree 3. Everything is perfect. So you can jump from one tongue to the other tongue. So let's say if I have those, I'll give a name this X. Let's say if I know this X already, so my total number will be what? 2 to the power of 10 minus in degree equal to 4 minus out degree equal to 4. But wait, I'm actually minus this part twice. So I need to add it back. So this is going to be my total number. You guys follow me? Yes or no? This is very important. Yes or no? You guys follow me? Please give me some feedback. Other guys? Yeah, this is an Amy question. It's a little bit difficult. So we need to understand we're on the same page. Okay? Okay, perfect. So that being said, we need to make sure who can tell me how can I calculate sometimes they're in degree 4, sometimes they're out degree 4. X equals to 160. That's perfect. Yes, I see somebody has the correct answer. Why? Why is 160? It's very understandable. Think about it. 1, 2, 3, 4, 5. You only have 5 tongues. Like I said, there's only one tongue can be in degree 5, in degree 4. There's only one tongue can be in out degree 4, right? So C51. From this 5 tongues, you pick up one tongue in degree 4. Let's say pick up this guy. So in degree 4, okay? Here, 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 here. And then from the remaining 4 tongues, you pick up one tongue out degree 4. Let's say I took this one. 1, 2, 3, 4, right? So this is in equal to 4. This is out equal to 4. So how many tongues are remaining? Like how many tongues? You have 1, 2, 3, 3 tongues, but how many rows remaining? You have 1, 2, 3, 4, 5, 6, 8. You have 8 tongues remaining. So basically you have like 3. Let's say this way, you have like 3. Yeah, you have like 3 rows, 3 tongues remaining, right? 3 tongues. Let's try to make it in this way. You have 3 tongues remaining. So that being said, for the remaining part, you do whatever you want to do. That's it. You have 3 tongues. You can do what kind of arrangement you want to do. Is that right? Or if you don't quite understand, you can do it from the other way. 2, 3, 4, 5. I already have 1 tongue. The in degree is 4. I have another tongue. The out degree is 4. I'm already using 7 rows. There are 10 minus 7 equals 3 rows remaining, which I do not really care. So the 3 rows will be 2 to the power of 3. I think this part is more understandable, right? Let's try to do the counting from the rows perspective. You have 3 rows remaining. You don't care whatever the direction. So it's 2 to the power of 3. So that being said, that's going to give you 160. So this guy goes to 160. 60. So the total number, 2 to the power of 10 minus in degree 4 minus out degree 4 plus back in degree 4 plus out degree 4. You're going to have the correct answer, 544. Okay, 544. This is the solution for this problem. So far, so good. This problem, think about it, we're not using something so complicated, right? Yeah, we use some graph theory, right? But we don't really ask you to prove the graph theory. Well, the most important thing for you guys to learn is how to do the casework. Like I said, if you're directly doing the positive way, there's so many cases. I don't think you can do it. So we actually do the reversely. We do it the other way around. Try to think about it. How are we going to do if something does not make sense? Does not make sense, basically two things. One is everything going out. One thing is everything going in. And the third thing is that everything going out plus everything going in. So these are the three cases. Case number 1, case number 2, case number 3. Okay? So plus you can do some Venn diagram to make sure that's how it works. So any questions? So out of all the things in this problem, the one thing don't understand, the total number is, okay, 2 to the power of 10. Yeah, because 1, 2, 3, 4, 5. Scroll down, okay. Okay, so let me try to understand it one more time. This is the, so you have how many rows? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay, 10 rows. You have 10 rows in total. This 10 rows you can do in this way, or you can do in this way, right? This is bidirectional. So that being said, means what? For every single road number 1, you have 2 ways. Road number 2, you also have 2 ways, this way or this way, going in, going out. And in total, you have 10 different tools. In order to finish the work, you need to construct all the 10 rows all together. So that's going to be 2 to the power of 10. That's the multiplication principle. Is it because there are 10 rows between the 5 towns, but it can only be one of the 2 directions? Yeah, exactly. They can be one of the 2 directions. So every single road, you have 2 ways to construct them. And in total, you have 2 to the power of 10 ways to construct them. So far, so good? Okay. If all good. Okay, let's go to a Canadian problem next. Okay, you see our lecture, we want to give you as much problem as possible from American, from Canadian. So let's go for a Canadian problem first. A Canadian problem here. This is a problem from 2010, Euclid, question number 8. Oi Lim tosses 3 fair coins and remove all the coins that come up as. George then toss the remaining coins of there if there is any. Determine the probability of George tosses heads. Tosses only one head or tosses heads? Can't remember like the real problem. I don't have it right in front of me. Tosses only one head. Only one head. Okay. there are two guys. The first one is Oelim. He tosses 3 fair coins. And every time when he basically figure out there's a up, he's going to remove it. Or maybe 3 times afterwards, he's going to remove all those heads up coins. And then George, the second person comes in, he's going to toss the remaining coins if there's any. And it's possible there's nothing, right? If everything is up and he removes everything, nothing for George. Okay, but here's the thing is George is going to come here to toss the coins which is remaining. Okay, so please determine the probability that George tosses only 1 head. Here we're going to use a little bit of probability, but I think for your level, this is not mysterious, right? You should know the basic concept of probability. Okay, this is a Canadian problem. You see this? You can see the complexity significantly reduced, right? We can see like in Chinese, 是一股清流啊, so straightforward compared with the American problem. Okay, an easy problem, we're still going to think about it. How are we going to do the casework? So basically, first people toss whatever he want to toss and remove all the heads. And then the second people come here. If there's any remaining, it's going to do another toss. And the question asks you to determine what is the probability that George tosses only 1 head. Okay? Casework. Who can tell me how would you like to do the? How are you going to classify them? This is like a problem which has different scenarios. How you can classify them into different scenarios. Yeah, I see people have the right answer right away. Very intuitively, the casework, you need to focus on the first person, Oelim, right? Oelim. So you want to see how many heads, how many tails that person tossed them out. He can have 0 heads. He can have only 1 head, 2 heads, 2 heads, and 3 heads, right? It's quite understandable. Okay, let's try to do this analysis. 0 heads. If there's a 0 heads, then there's no way for the second person to toss out any heads, right? So we can remove the first scenario. It's not going to give us, this is not going to help us any, right? If the first person tosses out 1 heads, so according to the basic probability concept, this is an independent event. You happen multiple times. We're going to review it later in our later course, okay? So what we're going to do is we're going to do C31. So basically, the first person tossed 3 times. You need to tell me out of this three times, each time you toss a head. As long as you toss a head, the tossing ahead probability is 50%. And you're tossing 2 tails. So the probability of tossing 2 tails is 1 over 2 perfect square. Is that right? If there is just 1 head, so George come to here, he basically toss it and then have the heads. The work is done. So if I have a line here, this is Oelim, this is George. So this is the probability for Oelim to toss out 1 head. And right afterwards, George needs to come here, toss 1 head, 50%. That's it. So this probability, 3 over 16. All good? 2 heads. C32. From this 3 times, each time that Oelim tossed out 2 heads, C32. And as long as he has 2 heads every single time, the heads is 50%, right? But twice should be 1 over 2 to the power of 2. And he also has a tail. The tail is also 50%. This is the probability for Oelim. And now it's George's turn. George has 2 coins. but he only has 1 coin tossed up as a head. So tell me, from these 2 coins, which one you choose to do the head? The head will give you 50%. And the remaining tail, you must also have 50%. Everything together, 3/16. So far, so good? Okay. 3 has. 3 has means C33 means you basically have has 3 times. Every time is 50%. You're so lucky. You have 3 times in a row. You have 50%. That's right. That's 1/8. And then it's George's turn. George, you have 3 has. Tell me which one you have your hat. You have 3 coins. Tell me which one you have your hat. As long as you have hat, 1/2. As long as you do not have hat, for twice, 1/2 square. That's going to give you 3/64. So these are the 3 scenarios, or say the 3 cases, right? We want to make sure there's no overlap and there's no oversight. These 3 scenarios, they're independent. No one is touching each other. And also, there's no overlap between the, I mean, there's no oversight. These 3 scenarios actually covers all the scenarios. The first scenario, 0 head, is not applicable to our case. We want at least 1 head. So these are all different casework. Of course, you want to add them together. You want to add them together. So 3/64, 3/16, 3/16, 27/64. So far, so good? I think this one is a lot more straightforward. Our Canadian exam is a lot more straightforward than the AMC, than like the AME2 problem I just mentioned. Oh, good? Yeah, we're extra silent today. If you have any questions, please let me know. Okay, so I can see your question. I'll be able to give you any explanations if you need.
Sir.
Yep.
Just a quick comment. It's about Chen's presentation. It was so inspirational. I just want to point that out.
Okay, perfect. Thank you. I have my fans. Thank you so much. All right. So did the other guys all good? Okay. If all good, let's go to another Chinese problem. We're gonna jump a little bit for the complexity. But trust me, this Chinese problem, I think it is actually more understandable than the AME problem because it does not use the graph theory you're not so familiar with. It just uses the casework. So we just want to show you how sometimes the casework, for this problem, it's only 3 cases, but in the next one, you're going to have almost 10 cases. But trust me, 10 cases, none of them coming from nowhere. They're gradually elaborated by your explanation. So let's have a look. This is, you see, this is like flip a coin, right? So those guys flip a coin. So the next problem I'm going to find you is also a Chinese problem, flipping a coin. This is 2001 Chinese Math Olympia question. But this is relatively easy problem for the Chinese Olympia. That's the coin flipping game. Let A equals to 0. And we start a coin flipping game. If you get heads, then A++. Okay, I'm using some programming language, A++, right? A plus 1. Otherwise, A minus minus means A minus 1, right? You need to stop the game in either of the following scenarios. Number one, as long as a equals to 3, you can stop. Or you totally flipped 7 times. Okay, so please determine when you stop the game, how many scenarios it could happen. Okay, I'll let you guys finish the writing. So this is a problem saying that you are basically playing a game. You flip your coin. If you get, at the very beginning, you have your counter A equals to 0. You flip your coins. As long as you got a head, A plus 1. As long as you got a tail, A minus 1. You just keep doing that again and again and again. So you need to stop whenever the following two scenarios, one of the following two scenarios is achieved. Either A go to 3, or even though A does not go to 3, but you totally flip 7 times, then you need to stop. So the question asks you, whenever you stop, please tell me how many scenarios it could happen. Okay, how many scenarios it could happen. Again, casework. Casework. Who can tell me? Just let's do a like some housey discussion. Who can tell me if one day we stopped? What is the scenario? Like in what kind of scenarios we just like stop? Try to abstract them, not to use the human language. Try to use the mathematical language. I'm just gonna tell maybe there are 2 scenarios, right? There are 2 scenarios. Who can tell more use the mathematical language in what kind of scenarios we can stop? Our game is over. So all your casework should be based on those analyses. Yeah, I see somebody has the correct answer. You know what? This is not a difficult question because the question already gave you, right? This is exactly the 2 scenarios you want to stop whenever your game is over, right? So basically, like I said, this is more like a human language. So let's try to put them into a mathematical language. So it means that if the game stops, it basically 2 scenarios. One scenario is A is equal to 3. However, the total times, let's say I use n to say that how many times you flip your coins, is actually lesser than 7, right? You didn't reach the 7 times upper limit, but you already get A equals 3. Or the other scenario is A is lesser or equal to 3, but your total scenario is already, total flipping times is already reached 7. A can be 3. A can be lesser than 3, but your total times is already 7. Is that right? This is quite understandable. So these are actually 2 big cases. However, for these 2 big cases, we are actually focusing on different stuff. So the first stuff whenever A is equal to 7, however, the total time is actually lesser than 7. So I need to do the casework. Focus on N, right? Because A is already 3. There's not too much to say about A, but N can be different. So my casework will focus on N. You guys follow me? Well, this part, N is already equal to 7. There's not too much to say regarding N. However, the casework will focus on A. Is that right? This is a little bit, so I think this is quite understandable, but it makes our life a little bit complicated because normally whenever we do the casework, we discuss same things, like our last Canadian problem. But this part is kind of different. Whenever you do A equals to 3, let's focus on different N's, casework on different N's. Whenever we do N equals to 7, let's do different casework, focus on A's. So that being said, my casework will be done on 2 different directions. All good? Okay. Can't A equals to 7 and N equals to 7 and A equals to 3 at the same time? Yes, they can. It is quite possible the 7th time you happen to get A equals to 3 and you happen to just hit your last limit. It is quite understandable, all right? It is quite possible. Okay, we're on the same page. Let's dive into the first scenario. If A is equal to 3, but I'm using lesser than 7 times. This case number 1, A equals to 3, well, case number is lesser than 7. So let's just have some discussion together. Who can tell me how many times you can flip your coins in order to make sure A equals to 3, well, N is lesser than 7? What are we going to do? Oh, only 2? I think should be more than 2. Should be more than 2, right? So let's have a look. Let's have a look. Yeah.
Is it 4?
Yeah, it's actually 2. Yeah, right. Yeah. Facilitation. Yeah, it's only 2. Yes, but like the total number is not 2, right? The total number is actually more scenarios. It's 2 cases. You're right. Let's have a look. Case number 1. I think in order to have A equals to 3, the minimum time you need to have is 3. You only have 1 flip. You can't have 3, right? So the minimum of N equals to 3. Every time is had. There's only 1 scenario. That's it. Second, what about N equals to 4? Is it possible? Can I flip 4 times and make sure A equals to 3? Not possible. Why? You have, let me change a different color. Whenever you flip 3 times, you make sure A is equal to 1. And then you flip an extra time, regardless it's 1, it's a tail or it's a head, it's going to be 3 plus 1 or 3 minus 1. So there's no way for you have 4 times flip, however, still maintain A equals to 3. Is it possible? So this is not going to happen. Can N equals to 5? Can N equals to 5? I think it's quite possible, right? When you have 1, 2, 3, 4 heads and 1 tail, then you will be able to make it happen. However, I don't think you can randomly let this heads and tails do whatever they want. For instance, when you have 3 heads in a row, head, your game is already over. You can't wait all the way to N equals to 5 to finish up your game. So who can tell me whenever n is equal to 5, you flip 5 times, and you want to make sure a equals to 3, how many scenarios you have in such case? Different students have different answer. Think about it. 5 has, 5 times 4 has 1 tail, right? As long as this 4 has are all together, they are actually consecutive. You need to think about it. Is it gonna okay or not? If at the beginning they're all consecutive, no, this is not gonna happen. If at the end they're consecutive, it is possible. You have a tail and then 4 has in a row, it is possible, but not the other way around, right? In this case, I don't think you have too much technologies, see permutation, combination, just enumeration, list them out. You only have head, tail, head, head, head. Head, head, tail, head, head. Tail, head, 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 head. I think only 3 scenarios. I can't find another scenario, but let me know if I'm missing one, but I think that's pretty much the case. You only have 3 scenarios. Number 4, can n equals to 6? Of course not, because it's the same logic. As long as it works for n equals to 5, whenever n equals to 6, it is impossible. You can either add 1 or subtract 1. There's no way for you to squeeze out. So far, so good? So that one is impossible. So far, so good? So that being said, you have 1, you have 3. In total, you have 4. This is the first scenario. You hit a equals to 3, but you're not hitting the upper limit 7 times. And you want to do your enumeration based on how many times, or your casework based on how many times. Let's go to the second part. You hit your upper limit, but you're not yet a equals to 3. That's going to be our case number 2. A is still lesser or equal to 3, but already n equals to 7. So that one is actually identical to what? N equals to 7, there's a lot. How can I do a little trick? Try to reduce the n a little bit. This is actually a tiny, tiny trick. But if you don't understand this trick, no problem. You just do another case scenario. But I think using the trick, you can actually make your life a little bit easier. Whenever n is equal to 7, you hit your upper limit, you just get a lesser or equal to 3. That's actually identical. Whenever n is equal to 6, you must have your a lesser than 3. Is that right? If you already get n equals to 6 and a equals to 3, your game is over. You don't have to go for the last one, right? Let's try to reverse. See, do you still remember I just mentioned a lot of counting and probability problem? You want to do a little bit reverse engineering. From the very end, let's move back, step back a little bit, right? That being said, whenever n is equal to 6, you must make sure a is lesser than 3. Okay, so let's have a look. N equals to 6, a less than 3. How are we going to make this arrangement? Because we mentioned, because we mentioned we're going to do some enumeration on this. So let's check it out. Case number 1, 6 times O has. Is it possible? Of course not, right? You're going to stop at the 3rd time. As long as n equals to 3, your game is over. 6 times O has. No. Second, 6 times 5 has. plus 1 tail. Is it possible? 5 heads plus 1 tail. Not possible. You don't have to waste your time do this allocation of head first, tail first. 5 heads already give a positive 5. 1 tail give you a negative 1. You put them together, you already positive 4. Like I mentioned, in order to make it happen, A must be lesser than 3, not even possible equal to 3. Here, already A is equal to 4. Forget about it. Number 3, 6 times 4 heads plus 2 tails. Is it possible or not? I think number-wise, 4 minus 2 equals to 2. Hey, that one makes sense, right? But you're probably going to do some magic to how to allocate those 4 heads and 2 tails. They cannot be too flexible. Let's say you have 4 heads on 4 heads in a row, then automatically you're out. You need to kind of arrange it to make sure how I can make it happen. Who can tell me? This is actually a challenging part. Who can tell me 4 heads plus 2 tails? How can I arrange them to make sure I can guess n equals to 6? Well, A is still lesser than 3. I'll give you 30 seconds. Think about it. This is the last problem of today's session. I'll give you some hint. Again, in our counting probability, if positively you directly do the solution, you can do it. Why don't you think about a negative way? Can you tell me in this 4 heads plus 2 tails, which scenarios are not okay? You use the total one, subtract the not okay ones, then you're good to go. Give you some time, think about it. This is a little bit difficult for this part. Think about it. I think the following 2 scenarios cannot make sense. First scenario is the first 3 times are all heads, right? This one we all know, 3 heads in a row. This is not going to happen. How many cases for this? You have 1, 2, 3, 4, 5, 6. You have 4 heads. If the first 3 is already heads, it means that you want to put another heads in the next 3, right? So that's going to be what? Say 3, 1. You have 3 scenarios, right? The first 3 are heads. The remaining 3, you just pick up 1 for the head. 3 scenarios. This is not going to happen. Second one is the first 5 times you cannot have 4 heads plus 1 tail. Is that right? In the first 5 times, as long as you have 4 heads plus 1 tail, you automatically reach A equals to 3. Your game is over. you can't do this. Is it right? First 5 times, 4 has 1 tail. That being said means what? It means 1, 2, 3, 4, 5. In the first 5 times, 6, you want to have 4 has, 1 tail, C5, 1. You just pick up 1 position as a tail. Your work is done. You guys follow me? So you have 1, 2, there are actually what? 8. These 8 scenarios are not possible. These 8 scenarios are not possible. Besides that, I think you can just do whatever you want. Right? So we try to think from the opposite. In total, you have what? 6 times 2 tails, C6, 2. Pick up 2 tails from the 6 times. You subtract this 8 like this mission impossible, right? So the remaining will be your total possible scenarios. So that's actually 7 scenarios. This is the most this is not a big number, but you need to think about it. This is the most challenging part. You need to think about it. Do it reversely. And you see, this is actually case in the case. Case in the case. Nation in the nation, right? Case in the case. We do casework within your casework. All good? Let's go to number 4. 6 times 4 had 2 tail. 6 times 3 had 3 tail. This is possible, right? 6 times 3 had 3 tail. Who can tell me how can you arrange this 3 had 3 tail? Three had 3 tail equals to 0, right? That's quite possible. Who can tell me how many scenarios 6 times 3 has 3 tail? Again, I think there are many, many, many scenarios, right? You just, on top of your head, you're going to think many scenarios. So maybe you will do it reversely. Can you do it reversely? Who can tell me which scenario does not work? Yeah, like Oliver mentioned, 3 has in a row. At the very beginning, 3 has in a row, automatically you're done. Besides that, do we have some other scenarios? Or all the other scenarios are acceptable? I think Ricky has the correct answer already. That's the only invalid scenario. Besides that, everyone is okay. So that being said, C6-3. Total scenario, 3 has 3 tails, whatever you name it, right? C6-3 minus only this one scenario's 3 in a row. 6 has at the very beginning. That one will give you 19 scenarios. All good? Number 5. 6 times and 2 has 4 tails. That's going to give you -2, right? For this guy, how many scenarios we can have? Is there any restriction for this? Like has cannot be adjacent, tails cannot be one after another, blah, blah, blah. There's no restriction, right? Like Chen mentioned, you do whatever you like. C, 6 to 15. Okay, we're getting there. But then, yeah, 6 times 1 head, 5 tails. That's going to give you -4, right? Again, no restriction. You do whatever you like. C, 6, 1, 6. Oh, yeah, there's another scenario. Sorry, I forget. 6 times O tails. That's still possible, right? O tails, right? O tails, still possible. That's going to be only one scenario. So in total, in your second scenario, we're talking about what? Whenever here, your upper limit is hit, but your numbers are still lesser. So you have 1, 2, 3, 4, 5, 6, 7. In total, you have 7 plus 19 plus 15 plus 6 plus 1 equals to 48 problems, 48 scenario. That being said means in the first 6 times, you want to make sure A is lesser than 3. You have 48 problems. A lot of students made a mistake. They stop from here. They think, okay, because this scenario is exactly identical as A is less or equal to 3 when N is equal to 7. So they say, okay, use this 48 plus the first scenario, we're good. A lot of students made mistake from here because this is only all the way to N equals to 6 and A is lesser than 3. So for the 7th time, actually can be tail and can be has. It doesn't impact our final solution. Is that right? Even though we say these two scenarios, they're identical, but not necessarily means their total scenarios are the same, because the 7th time you can have a tail, you can have a head. So therefore, if consider the 7th time, you're going to have 48 times 2 equals to 96 total scenarios. You guys follow me? So in total, you have what? Still remember, we have 2 scenarios, 2 cases. This is our case number 1. We have what? 4. This is our case number 2. We have 96. So in total, we have 96 plus 4 equals to 100. That is the solution for this problem. I think this problem is actually using a lot for this casework. Normally, you won't have even more difficult problem than this casework. The problem per se is not very difficult, but it doesn't use the graph theory, blah, blah, blah. But you really have to understand the casework in order to make it work. Why I multiple by 2? Yeah, like I mentioned, it is okay. You all the way come to here. All the way come to here, what were we talking about? We're talking about all the way here. We're talking about if you throw 6 times and your total A value is lesser than 3, then you have 48 scenarios. But you don't count the 7th time. The game will stop at the 7th time. The 7th time can be tail, can be has. So therefore, you need a times 2 for the 7th time. Even though we say these 2 scenarios, they're kind of equivalent, but equivalent for your analysis, for your casework, but not equivalent for your final scenarios. So this is the difficult part for this problem as well. It's a Chinese MO. This is not an easy peasy problem for sure. For 白菜啊，是不是? Okay, so there must have a lot of like tricks there to make it more challenging than otherwise. Okay, any more questions? Parfait. In that time, I think we actually wrap up our first lecture. Our first lecture, we don't dive into the permutation, combination, blah, blah, blah. We just try to focus on the base scenario, how to do our counting. Our counting, like I said, the most important one is doing the enumeration. Enumeration is nothing doing the casework. So how to do the casework, unfortunately, I can't give you a black and white reason, like a black and white rule. It's always case by case. But regardless, we know some scenarios. Sometimes you focus on the, flip a coins. We focus on how many times. And moving the path, we focus might go to the A, go to the B, go to the C, right? So on and so forth. So the casework, the most important thing is you want to make sure there's no overlap. There's no oversight. If you put them together, it covers all the scenarios. If you check them one by one, there's no interference between one and another. That's actually where we come from for the casework problem. So hopefully, some easy, some not necessarily so easy, but some brief problems can give you guys a quick heads up, help you guys understand how to do the casework. And like I said, the next lecture, we're going to continue, help you guys review some basic concepts of the counting and probabilities, and we give you more interesting problems and help you guys understand. All right, that's pretty much for today's lecture. And that's it. Any more questions for me? All good? In that case, we'll upload the assignment to our Google Classroom, and then we'll take it from there. All right. Thank you, guys. I'll see you guys next week. Enjoy the rest of your weekend. Bye.